this was the last problem then, the race car. And this problem states whether we have to find the position. Uh, uh, Basically, we are given with the position, and we have to find the sequence, the minimum sequence that we need of instructions. So there are two instructions. There is one instruction A for accelerate and R for reverse. So whenever we are giving an instruction A, then it does mean the position will be increased by the speed, and speed will be equal to speed into 2. The speed will get multiplied twice. So and if the instruction is R, then speed will become -1 if the speed is positive. Otherwise, speed will become 1, and our position will remain the same. It won't change. So we will be given a target value. Let's say the target is 3. So it does mean we have to reach to the position 3. And to reach the position 3, what will be the shortest sequence required? Like to reach position 3, the shortest sequence required is AA. So initially we will start from the position 0, and our speed will be 1. So we'll reach to the position 1. Then after reaching to the position 1, our speed will be 1 into 2. That's 2. So again, we will add back with the position, and we will reach to the position number 3. So ultimately, we have to find out the shortest sequence, and the shortest sequence in such way that we reach to the target position. Is the question clear?
Yeah.
Yes, it's clear.
So as I see the constant values, I can guess, yeah, it's a question from the dynamic programming. I haven't solved it. Anyone else with any approach?
I tried it, but it's failing for a couple of scenarios. So what I did was, just took few samples like continuous AAs, and then found out like all the numbers are in the form of 2 raised to power I minus 1. And what I did was just took a number, like let's suppose 156, or suppose let's say 128. Then I tried to find the nearest number in the form of 2 raised to power I minus 1. So let's say for 128, it becomes 127 plus 1. So there are two ways we can reach 128. Either it is 127 plus 1 or 255 minus, I think it's 97 or something. Then I tried to, so 127 can directly be reached from the A steps, or the 2 raised to power I minus 1 I steps. And then recursively try to call what is the minimum number of steps that I can reach, that I can use to find 1, which is the remaining part. It is working for some scenarios, but for a scenario like 5, it's not working. So seems like I am not able to find the correct sequence right now, but seems like there's some other logic that we have to see.
I don't know if my logic will work or not, but it's a simple subsequence question. Like we can use the subsequence method, as in for every call, every position, I'll make 2 calls. One will be for A and one will be for R. And from both the calls, I'll say that give me the minimum length of the string, and I'll output it. So directly I'll get the answer. Like I don't think that we're even required to use deep. It won't give any TLE error.
Can you please say once again? Because
Okay, let's start for the first example. I'm at 0. So from the 0th call, I'll say that you either go with the A part or go with the reverse part. Okay. So at the A part, as you can see, my speed will be 2, and it will get multiplied. My position will increase and my speed will get multiplied by 2. Then from the second call, I'll again make 2 calls, one for A and one for R. And
yeah,
I'll see that if I'm getting if I'm equal to like my target position, then I'll return that path. I'll make a class wherein I'll store the size and my target position. That's all.
yeah, I got it. Yeah.
So that solution, I think, will be 2 raised to power n, right? or yeah, 2 to 5.
Yeah.
Okay.
And the constraints, yeah. So I guess we will be getting a tail. We might be getting a tail for this because
Yes, I think Tanmay's solution would work, but just that it's not optimum solution because we are exploring all the possibilities, which would
yeah.
be, yeah, so which might give a TLE here.
Any other approach like DFS, BFS, it might work, I guess.
It's like similar to DFS, BFS both. It's just the opposite way out. I'm starting from 0 and DFS will start from 3 and start exploring the reverse thing. I
Okay.
guess there'll be some DP condition that could be applied.
Anybody solve this? Try to solve this.
No, she's not from my side.
Okay. So I think the the possibilities, like if we get a A, then R, then again for the next iteration we will check for A and R. I think that will work, but I'm not sure about the time complexity of that. Okay. Yes.
Anyone else has any? Sorry.
Hello.
Yes. Yes.
I tried solving this question using BFS. It is similar to Tanmay's approach, but I think Tanmay's is more of a recursion-based approach. It's a DFS-based approach where you actually go, you follow a particular path and it leads and you see where it leads you to. But BFS is more restrictive in that sense. So as Tanmay said, like we begin from our source, and then we have two options. We can do either accelerate or we can do the R option, that for the decelerate. And then for counting the number of BFS grows in the form of a layered mode, right? Like first you have one vertex and then you'll have two vertex that belong to the second layer. Then subsequently four nodes that could be discovered in the third move. So I use generally for these questions I use two queues, like the where one queue contains the vertices which are being of one layer and the other queue contains the vertices of other layer. This approach generally works, but I'm getting PLE, so I'm trying to optimize the data. I was using pair to identify the combination of position and display. So I'm trying to use string something like that. I think at the discussion forum, and to have used the same approach. So I'll post it in the group if I get unexpected from this. I'll post my code.
Okay. So you try with your pair approach, and then you you can post your code in the channel.
Yeah, sure.
Yeah. So do you have any other questions or approaches, or shall we end the session?
Actually, this is Vivek. I have a few quick ones to kind of add on top of this. Right. So one is, would the question be any different if you start from the beginning or the end? Like, would you change your approach significantly if you started from the destination and then you're working backwards towards the origin? That is open for everyone.
Vivek, I didn't get you. What do you mean by like origin destination on this?
You have to reach a target location, right? That's the goal here.
Right.
And your starting point
Right.
is position 0.
Mm-hmm.
And you can start your computation from position 0 and essentially say that if I do accelerate, and then reverse, then I get the answer. Or can you do it from the end? In this case, I want to hear what people are thinking, but generally for such traversal and exploring problem, there's always worth looking whether you can actually start from the end as well. Here you cannot,
Yeah, Vivek.
because
Mm-hmm.
why can't you start from the end here? Because we wouldn't know what the velocity is at that time, right? We don't know the speed at that point.
Yeah.
So this is only forward looking, but typically in a maze question, even reverse actually works. Like when you're actually solving a maze, as a kid, when we had all these maze questions, right? Where you have a starting point and ending point. If you actually start from the end and try to solve the maze, it's much faster.
I guess I got the DP approach. I don't know if it's DP approach or not. I just used basic mathematics, and I don't know. I'm not sure that if it'll work, but I guess it should work. Basically, if we just go on with the A's, it's gonna become a AGP series, okay? Arithmetic geometric progression series. So we have the expression for it. We already know the expression for it. And for in case I'm having all the numbers, like as in I'll be having 0, 1, 3. Is it still working? Okay.
Yeah, he just turned on the screen share. You can share your screen if you want.
I won't be able to write. That's fine. I'm saying that I'll be having numbers like 0, 1, 3, 7, 13, 21. It's a arithmetic geometric progression series. Okay. So I directly know that what will be the positions from wherein I'll have to reverse. I know the speeds. Speed is just a geometric progression, and the position is following an AGP series. So for in case the question was like I had a position. I guess it was I had a target of 6. So I knew at fourth position, at the fourth interval, that fourth accelerating part, my position will be 7. And I'll have to reverse from there only. So basically, you can directly reach the nearest target position and then use the reversing conditions to get the answer. It will be like making our approach, making our solution in order of 1 or so.
But that's not, no, yeah, that's good. Log n of sorts, right? Because you're doubling the speed every time. So it's not order of 1, but it's log n. Like to compute the series, you will have to do a log n, right?
How come it's log n? It's just a basic mathematics calculation of multiplication division, right?
But that's
Tanmay, that will work if you have a number in the form of 2 raised to power I minus 1. But what about a number which is not exactly in that form? Like let's take an example of 5.
Yeah, that's what I said. In this series, I'm having numbers such as 3 and 7.
Right.
So I'll go on with my series. Okay, yeah, it's log n. I'll go on with my series and I'll look the nearest number to 5. It's either 3, but at the point wherein I'll get a number greater than 5, I'll start adding R's to my answer and I'll get the answer if it's reachable.
No, but hang on one second, right? The reverse is like once you reverse, you can also further accelerate in the back, right?
Yeah.
So in some scenarios, you don't have to. You could either overshoot. Let's assume that the way this is that you're actually overshooting it, significant or just subtly. Then what will happen is that let's assume that you reach 1000 and 1001 was the answer. So because of the acceleration, you'll probably go all the way to 2000. And now you're backtracking from 2000 using reverse and accelerates, right? Instead, it'll probably be a better idea to go from 1000 to like 999 and then go forward. So your answer is always not to overshoot and come back, but you may also undershoot and then do a quick reverse and then accelerate, right? Does that make sense? Like both are reasonable answers, and it's also possible that you may actually have a better answer by doing it by actually resetting yourself at 200 instead of 1000 when the actual answer is 1001.
Does Tanmay solution give us the minimum sequence, because I think the result asked was a minimum sequence that is for that should be the
Correct.
answer.
And that minimum sequence may actually happen with a different equation. Like what you're doing is a greedy approach.
Yes, that's what I also feel.
Yeah, and that's
So
probably not the may or may not actually work.
what I'm thinking of doing is, for in case I'm having 1,000, I'll reach two numbers. One is lesser than 1,000 and one is more than 1,000.
Correct.
So
The more than 1,000 makes
I'll,
sense. The more than 1,000, you're just doing a reverse, and then you're just trying to get there, right? That makes sense.
I'll just try and approach it. Like I'm having two approaches in my mind right now. One is that for two numbers, for in case I got 1,001 and I got 999, I'll start my subsequence from there.
Mm-hmm.
And the other thing that I'm thinking is that I told you that I'll overshoot from 1,000 and I'll go backwards. I'll try it and let you know. I just came back home right now, so I didn't get the time to try these questions.
Got it. So how about, I think we talked about dynamic programming earlier. The only thing that I was trying to understand was like, I don't know if I heard that in the conversation discussion was once you are on the reverse direction, you can actually remap the entire question, right? So if you, for whatever the example we talked about, if you overshoot to 1,000 and go to 2,000, for example, and then at that point, if you hit the reverse, you're actually essentially starting in the reverse. Right, which means that now you need to go 999 distance at a speed of 1, and your position is essentially like, you can reverse or remap your origin to that 2,000 point becomes your new 0, and your velocity becomes like +1 instead of -1, even though it's like towards the left, and the destination is 999 instead of 1,001 because you're doing a remapping exercise. And then you can just use whatever solution that you had before for this one.
So is that like a top-down solution?
No, it is not a top-down solution. It is still like a bottom-up solution. You're still starting from the starting point and then you're going ahead. Essentially the way it is working is that you need to create like a memoized array of what is the fastest way to reach point X. That's it. Okay.
So
it's a two-dimensional thing, right?
Sorry.
It's a two-dimensional array of what is the fastest way to reach point X with speed Y, essentially, which is what the memoization technique that you talked about. The only thing that I was saying was that you can also remap the reverse algorithm in such a way that it actually works backwards, works for you.
Yes, got it. So we are like imagining the problem from the opposite end, but it's still the bottom-up approach. Yeah, got it.
That is correct. There is one thing that I wanted to actually highlight in this one was that I didn't think I heard the discussion on this one. Is that one of the concerns that I have, especially with the Tanmay's approach, is that what if I actually give you a number? I mean, I know the constraints are actually much smaller here. What if I increase the constraints to as close to the integer max as possible? Right. So then in that case, you may have a real legal solution or a valid solution that is there, which might even be better and faster and quicker. But when you do speed equal to speed times 2, right, you may actually overflow the integer maximum. In like 31 steps, you will actually overflow the maximum, right? So we may have to consider integer out of bounds, especially when you're actually trying to multiply numbers. Like especially if you're like, you constantly keep multiplying or you keep adding, you need to keep that in account. So just remember that. That make sense?
Doesn't that make sense? Could you please approach the repeat the DP approach that you told just right now?
Sure. So let's do the DP approach first. So the DP approach is essentially what we're trying to do is we're trying to for all possible solutions that you have, essentially what we're saying is that given point 0, right? What is the in how many steps can you reach there? That's essentially point 0 with speed 1. How many? What's the minimum steps to get there? It's just 0, right? You do nothing. You're there already. Correct?
Yeah.
Okay, what is the point of getting, like, how do you get to point 1 with step 1 or with speed 1?
Simple A.
Just accelerate once, because then the position becomes position plus 1, and then the speed becomes 2 at that point of time, right? And what is the thing of getting to point 3 with speed 4? That is also like 2 A's and so on, right?
Okay.
And then you can keep, if you do that, what you're building your DP table is essentially, in one axis it is the positions, in the other axis it is the speed.
Okay.
Got it? Now
Got it.
the thing is that on the reverse, right? If you're trying to reverse the equation, you can actually copy from the DP itself. Like if your speed is -1 and your current position is say 100, right? Then you can do a remapping exercise of what the origin looks like and what the direction of the speed is. So you can, your DP table will never contain negative speeds.
Yeah, I got it. Somewhat got it.
Like you'll never have negative speeds in your DP table,
Yeah, that's true.
right? Because
Okay.
the equation is reasonably symmetric at that point of time, right? So you can just, you can do that. So that's the only thing there, and then keep computing till you essentially reach the target. And you don't really care about which speed that you are at that point of time, right? You don't have to be at a specific speed to the target.
Okay, got it.
Vivek, I have just one doubt. The approach that I tried, I'll just share my screen. I'm just not able to understand where it's wrong or what's wrong with that. Why it is not able to give the solution.
Go for it.
What I did was, just let's take a number 156. So we can reach 156 in two forms, two ways if I consider the sequence of form 2 raised to power I minus 1. So like 127 plus 29 or 255 minus 99. And then what I did was, this number can be directly, got in I steps, which is IAs. And then, this one I again broke down into the next steps, like it can be given from 31 minus 2 or 15.4. Kind of, creating that memorization table. Like if I reach 29 in suppose 4 steps or 5 steps, so I can reuse it if I get it somewhere else. But, it works for a couple of numbers, but for a few numbers it's not working. Like for 5, it's not giving the correct answer. For me, it's coming around 9, whereas the answer is around 8.
And why do you think that is? I mean, I think I know the answer why, but why do you think that is?
I believe I'm not taking into consideration the speed part. I think that's the, but I'm not able to figure out where I would put that.
I don't think it's the speed, right? The speed is reset to 1 or -1 because of the reverse. So that's not the problem. The challenge that you have is that you may actually have, again, as I said, right? In this particular case, can you write the AGP?
Yeah.
It starts with 1, then 3. Oh, 0, 1, 3. That's the speed, right? Fantastic. So now the problem that you have here is that what makes you certain that you have to do a 127 or 127 and forwards or 255 and backwards? Why would you not do a 63, a quick reverse, and then jump forwards? Like do 2 quick reverses after 63 and then jump forwards. Or like 31 and do a reverse and then 2 reverses.
Oh, you're saying resetting the speed at 63 instead of 127.
Exactly, right?
Oh, yeah.
And that's what you're missing here.
Got it.
Okay, which is why the DP approach is a little crappy here, but BFS is probably the easiest, because at any point of time, the decision making for you is either you can do an accelerate or you can do a reverse. So you can just do a BFS on that one, and then keep going, right? That's the fastest way of actually solving this, quickest way of solving this. DP works, but you just have to think about how to structure that. It's a little
Yeah,
harder.
and that still will be at among these points only, right?
For which one?
For taking a reverse action and then moving forward, it will be one of those.
Yeah, but but it resets the equation completely, right? Let's assume you don't have to do two reversals.
It will reset the equation. I'm just trying to figure out how many steps or how many branches it will take, like BFS. So which will essentially.
But you could do a reverse, accelerate, and then a reverse. And that's probably still better, because what might happen is that, like, as you're resetting, you don't have to reset it only to -1, +1. You could reset, or you could reverse, and you could go back a little. So you could go from 63. If you do a reverse, you're going to 62, right? No, you just stay at the same place as a -1 value.
No, if I do one reverse, if I accelerate after that, I'll go in the backward direction.
Correct. But you may actually go twice or thrice in the backward direction, because that might give you more bang for the buck. Right?
So this is interesting. Hi, this is Bhavesh. So Vivek, what you said, that is interesting. So if we do BFS, then can we apply the shortest path algorithm?
Yeah, that's it. So at any point of time, you can only point of time you can do A or R. That's it. That's
exactly. So
right?
So from I'll start with initial position. I'll do A and R, and then basically keep expanding it. If I'm going beyond the desired result, then probably I will.
No, you can't stop. You have to still continue. It's just BFS. So if you find a solution that is actually it is possible, given his example, right? 255 minus 99. So you may overshoot and then do a reverse and come back from the reverse direction. You can do that too.
I see, but DFS or BFS? I was thinking BFS.
Breadth first search, yes. It has to be breadth.
Okay. All right. Okay.
So that's all. Like, the simplest solution for this one would be a BFS, because the question says that find the shortest commands for the race car, right? So that's the easiest answer. But if you want to do a dynamic programming, it kind of works, but the question has a bunch of different nuances that actually makes it harder. The only additional thing I wanted to tell people, which I think I mentioned it, but I don't think we caught on to it as much, was this question may not need it, but you actually have problems with integer overflow if there are concerns. So let me ask you slightly different questions and see if we have about 10 minutes, right? So let's actually, any other questions on this question alone? Going once, going twice. All right. So how many of you are familiar with Collard's conjecture?
Can you please repeat? Familiar with?
Collard's conjecture. I've mentioned that in the chat. If you the name.
Okay.
Yes, no, maybe. You can look at it in Wikipedia if you want. Collard's conjecture is actually a pretty straightforward conjecture, where what it says is that given a number in sequence, you start with any number. If the number is even, then you just divide it by 2, right? So if like f of 16, the next value essentially is 8, and then after 8 it is 4. After 4 it is 2. After 2 it is 1. If the number is odd, which is like 1, then essentially you replace it with 3n plus 1. Okay, that's it. So it's either n by 2 if even, and it's 3n plus 1 if odd. Okay, so for every time the number is even, it actually reduces, and 3n plus 1 will make it like even, right? If an odd number, 3 times an odd number plus 1 will be an even number. So again, it will go down, and then that may be an odd number, and then it may go up and things like that. So the Collard's conjecture is that any natural number will actually reduce to 0 or reduce to 1 and always. So if I think if you look at the example in Wikipedia, it actually gives you the example. Let me just paste one of the examples here. Is that if you have sequence like n starts with 12, then since it's 12, 12 by 2 is 6. Since it's 6, 6 by 2 is 3. Since it's 3, it's actually 3 times 3 is 9. 9 plus 1 is 10. So it's 10. And then 10 becomes 5. 5 becomes 15 plus 1 is 16. 16 becomes 16, 8, 4, 2, 1. And then 1 again becomes 4. And it will actually be flipping between 1 and 4 after that. Right? 1, 4, 2, 1, 1, 4, 2, 1, 1, 4, 2, 1. Right? It will keep going through that loop. So the question was that, like, how would you test this collapse conjecture out? And can you prove that for all, like say integer, 32-bit integers, collapse conjecture is actually holding true? What do you guys think? When I saw the race car problem, it kind of triggered this collapse conjecture bit for me. Any thoughts? Folks are quiet.
Actually performing that sequence like based on the equation like n by 2, 3 and 1 till it becomes 1, but I don't know if it may be a very long sequence.
It will be depending on the number. Like I've given you one example, which is 12. I can give you another example, which is this one. And you can actually, if you just search for like collapse JavaScript or something like that, there'll be somebody who must have written a program.
I have a doubt. What do we mean by proving it for 32-bit integers? Proving that collapse conjecture is true.
So the question that the collapse conjecture is that given any natural number, it will always reduce to 1. The sequence will always end at, it will become 1. So tell me, like essentially tell me if it's true. Tell me for like, how will you compute the collapse sequence or for every number and make sure that every natural number like 1 to 2 power 31 minus 1, all of them actually reduce to a smaller number. Yeah, reduce to 1 basically.
Would it be like starting from the smaller number and adding to like memorize the result? So basically, whenever you are at a bigger number, you divide it by 2 and see if that already exists in your memorization.
Can you say that one more time? Sorry, my audio just cut off.
So I want to say that would it be like something like starting from the smallest number and then memorizing the result? So basically, since we know that 1 does follow it, right? So just memorizing the result, 2 follows it, 4 follows it. So whenever we go to a bigger number, like when I'm at 8, if I just divide it by 2 and see what my result is, if it already exists in my memorization, then I'm good with it.
But you realize that how much memory you need, right? You need 2 power 31.
That is true.
And that's not really tenable.
But but Vivek, we want to find out if the all 32-bit integer are covered or not, right?
That's all you want to find out, correct?
I see. So basically,
hey, can you go on mute? We're getting feedback from you.
So basically, we can, start from any number and we might overshoot and then come back in the range, right, to reach 1. For example, I'm at integer max and I might have to double and then
that is correct. That is the problem. So there is no guarantee that even like one of the simplest hacks that people explained was saying, why don't I use longs as my collapse sequence keeper, and then I will actually just use that. But there is no guarantee that that all integers are resolvable in the long space.
I think if we could use something similar to sieve of Erasmus, like we'll go from
C
one
C
sieve of
won't work, right?
Erasmus.
No, C won't work in this game. That's a good concept. So the way you want to, so a couple of things, right? So fantastic point. So I think what just like how Jaspir mentioned, one thing you can do is you can create what is called like a high water mark. And the idea is that you create a line that says like all numbers below this converge to 0 or converge to 1. I know that, right? And every number below k or below x actually converges. You know that. So then what you can do is for x plus 1, you keep doing whatever you are trying to do. And then when it actually it falls below x, right? You know that that is now resolved.
Yeah.
So you, and then you go to x plus 2 because now the high water mark is moved to x plus 1. So then you look at x plus 2. As long as x plus 2's sequence falls below x plus 1, you are good. But the problem with this is that it actually goes, when it goes high, it can go super far out in the future. So there's no guarantee that it'll actually for sure it'll overflow the integer space, because a number which is an odd number which is maxent, very close to maxent, will definitely maxent itself, for example, there is an odd number, so 3n plus 1 will actually fail, right? It'll be out of range. So one thing that you can cheat by saying I'll use long space, but then the problem with that is that there is no guarantee that that can be resolved in the long space. I have solved this, I've done this question. Yes, it can be done in long space. It's okay. It's not an issue. It works. But like again, the same thing. What if I were to say, fine, resolve it for all 64-bit integers, and you run this, can you actually go to like long or 128-bit integers, and will it be resolved? I don't know. There is no guarantee that you can't just simply increase the width of the integer and make this work. So anyway, it's a good question. I think it's just the idea here is just to take like a leaf from different types of questions and whatnot. Whenever you see one question, just see if there are other questions which are there as well. So we've got 2 minutes. I want to